We're waiting for people to come in after lab. So hopefully everybody's here. So recap where we left off so that we can continue with the data analysis. Okay. What's the difference between accuracy and precision, April?
Accuracy is like how close it is to like the actual true value, and precision is like how close the data is to.
Yes, exactly. Precision is how close are your replication of the same sample. So the results of your replications, how close they are to each other, and accuracy, how close they are, the value is to the true value or the reference value. Okay, what's the difference between threshold and sensitivity? Threshold of the method, Brigitte?
Threshold is the minimum level that an equipment can detect, and sensitivity is the smallest change that.
Exactly. So the threshold is the minimum amount or value or absorption or minimum measure that an equipment or a method can detect. And sensitivity is the minimum or the smallest change that an equipment or a method can detect between samples. So the smallest difference or the smallest change that the method can detect. In what case, coefficient of variation is better measure of precision than standard deviation? When do we rely more on coefficient of variation and why? Do you remember what is coefficient of variation in terms of your equation? Coefficient of variation equals? You can look back at your notes. Michelle.
Yeah, standard deviation divided by the mean.
So yes, coefficient of variation is the standard deviation divided by the mean. When we divide by the mean, that means we're correcting for the size or magnitude of your mean. By correcting for the size, then we can get an actual variance. So if we have two samples of different magnitude in a certain component, like the example we gave last time, difference in protein content. One sample is 10% or lower in protein, and another sample is above 90% protein. So there are different size of measurement. So when we divide by the SD by the size, by your mean, then we get a better estimation of your variation, and that is the coefficient of variance. The others are related to what I'm going to continue to cover today. So we have so many sources of errors. I mean, unbelievable. And you're very good at creating your own sources of errors in the lab. There's always something new that we encounter. But the common ones are what we call a systematic error. For once, it's not your particular direct fault. It would be that an instrument is not calibrated, more specifically a balance or a mechanical pipette. So basically a mechanical pipette you'll see in the lab is programmed to pipette or withdraw a certain volume of liquid. So if we think that it is withdrawing 1 ml of liquid, and in fact it's withdrawing 0.9 ml of liquid, it messes up your results. So that is a systematic error. You're always taking 0.9 instead of 1 ml. This is Kain. So yes, so it needs calibration. So we need to calibrate it so that it will come, when we say 1 ml, it will withdraw exactly 1 ml. So this error is systematic. It's not a particular experimental error. Random error can be coming from, for example, utilization of different balances for the same measurement. For example, you will be measuring moisture content in your food, and then you need to measure first the weight of your empty dish that you're going to weigh in your sample. And then you're going to weigh in your sample, and then you put it in an oven. The next day you come, you take it out, and then you weigh it again to determine the difference in weight, so that the difference would be moisture. If you use on one day that one particular balance, and you come the next day and you use a different balance, you are incorporating an error coming from utilizing different balances with their own different errors, experimental error. Another example of a random error is basically you as an experimenter. So that means you have a different way of pipetting, different way of looking at things. If we're measuring, if we're doing a titration, so the way you look and you can read the meniscus is different from another person. The way you transfer is different than another person transferring from a volumetric flask to a beaker. So there are slight errors that you introduce. We call it experimental errors. Blunders. These are big mix-ups or screw-ups. So like titrating with the wrong reagent, or adding instead of adding an acid to digest, you added a base, for example, or a dilute type of acid. So just something that you mistakenly introduced in your sample or in your experiment that completely screwed up your results or skewed your results. So these are the different categories. Okay, so we talked about sensitivity and detection limit, in other words, threshold, and we also talked about specificity last time. From what we just talked about, which one of this or which answer is correct? Maddie. D.
C.
What did you say?
C.
C. Oh, okay. Yes. C. So detecting a minor change in constituent, or the smallest change or the smallest difference between samples. A low threshold, that means low detection limit. Detection of only one constituent is specificity. Okay. In many experiments throughout the semester, you will be plotting standard curves, because oftentimes you're looking for a concentration. And with looking for a concentration, often we're using absorption. When you do atomic absorption, for example, we're going to be using the atomic absorption instrument that gives you the absorption of a certain mineral. And then you run standards with known concentrations and you measure absorption of that. Then you plot your known concentrations and the absorption, and then you measure the absorption of your unknown sample, and you use the equation of the line to predict that concentration. So a lot of times you're going to be using standard curves. For other than the AA, you will be using standard curve for the total carbohydrate assay. We will be doing a calorimetric assay for a protein, the Bradford assay. You will be using standard curves. So a lot of different assays, we will be using known concentrations and then measure absorption and then detect concentration or predict concentration in an unknown sample. So yes, so standard curve, we often use it to determine unknown concentrations in our samples. So in order to detect the concentration, we need to have the concentration of the substance proportional to the measurement. That means you need to have some relationship to the measurement, and in our case, it's mostly absorbance measurement. So we need to have linear regression. It's not always linear, but in our case, in food analysis, most of our analyses are linear regression. That means we have a linear line, the data fits a straight line, and then we get a prediction equation. And then with the prediction equation, the higher the R squared, the higher is the power of prediction. And then you can use the Y value, which is the absorption, to determine the X value, which is your concentration. So your independent variable is your X-axis, and that is often your concentration of your standards. So you prepare your standards, you know the concentration of your standard, then you measure the dependent variable, which you plot on the y-axis. So the dependent variable is oftentimes, in our case, absorption. So you measure the absorption, you know the concentration, and then you plot your data and fit it to a straight line doing linear regression. So we have what is known correlation coefficient, designated by R. This is how good the data conforms to a straight line, fits a straight line. Now the coefficient of determination, which is the R squared, is how much of the measurement is explained by the regression or the line or the equation of the line, or that, in other words, how strong is your prediction. This is a typical standard curve that you would actually be plotting for bovine serum albumin, which is a protein standard that we will be using for the Bradford assay that we talked about, measuring protein content. So we prepare a bovine serum albumin standard under different concentrations. The more the concentrations, the better. You get better prediction when you have more concentration. But typically, you don't want obviously anything less than 3. And ideally 5 would be good. More than 5 is good. And then you prepare your standards. And then you measure absorption. And then you plot the data. And then you have your equation of the line. Y is your absorption, X is your concentration. When you have your sample, you will have the absorption, and then you solve, and you get the concentration in your sample. So we'll walk you through that in the lab when the time comes. The first exposure to standard curve will be in the caffeine lab when we measure the caffeine content, the HPLC, and we use caffeine standards to do that. Here's where I'm going to spend a little bit more time for refresher, because all you're going to do is report numbers in your lab report for the rest of the semester, other than the first lab report with nutrition labeling. So with the reporting of the numbers, you want to make sure that you're reporting the right or approximately the right significant figures. And you don't want to have a number with 10 decimal points. It's not logical. You want to make sure to report the correct decimal point based on the sensitivity of your analytical tools, whether it is a pipette or whether it is a volumetric flask or a balance, analytical balance, or HPLC or a spectrophotometer. So each of these instruments have their own sensitivity and accuracy. So I'm going to remind you, refresher, from middle school maybe, if not high school. I have some numbers here that I use every year because it's easy instead of me coming up with numbers each time. Okay, so let's remember together significant figures. How many significant figures? 1. Good. How many significant figures? 4. Great. 3. So anything here does not count. All right. 3. Anything after, all the zeros after the decimal point, when you have the number here, counts. But if you have 0.00102, these don't count. These count. Okay. Great. You get the idea, don't you? And this one can be, if we want to put it in then it's still 4. Okay. If you do 7 times 10 to the 3, actually, no, If you do 7 times 10 to the 2, then it's one number, one significant. Okay? So you got that again. Alright, that is very simple, isn't it? Okay, it gets much complicated, more complicated. Okay. Let's say you are going to calculate a certain measure using multiplication, which you'll do that a lot. So we have a lot of equations where you're going to multiply figures. Okay, so let's say you have this. Okay. And then the actual answer to this is so when you do an equation, first thing you need to do is just put the numbers as they are. Then round to the correct significant figures. Don't round before you get the final answer. Once you get the final answer, then think about what should it be? How many significant figures should my answer be based on multiplying these numbers? 2. Thank you. So the value of the least significant figure. So I have 2 significant figures. This is the value that limits my significant figures. So my number would be rounded to this. Good. Now, if I have an addition or a subtraction equation, so for instance, so I'm adding 2 values, like that. I got this. Okay. Alright. So how would my value be reported? 2 number after the decimal. So in this case, when I have decimal point, I go not necessarily by the significant figures, but more by how many numbers after the decimal do I have, because this indicates sensitivity. Alright, so I import it as this. So it ends up to be 4 significant figures, but 2 decimal points, because I have the least decimal points this time. Right. It gets a little bit more complicated. Life is complicated. Okay. Let's say what you're going to do, you determine caffeine concentration in one of your beverages, tea, Coca-Cola, Pepsi, I don't know what it is, but you've gotten a value that tells you you have a concentration of 43.5 micrograms per milliliter. This is the value you've gotten of caffeine. But this is the reading you've got off of your standard curve. But you'll notice most of the time we do dilutions. We do dilutions so that your reading fits your standard curve. It's not too concentrated. It lies out of the standard curve. You want to make sure it is within your linear prediction. So we dilute. So this sample has been diluted 50 times. That means you've taken 1 milliliter from your beverage, you added 49 milliliters of water, and in a volumetric flask. So you diluted it 50 times. So what you normally do to get the correct answer is what? What do you do to get the correct answer? It's diluted 50 times, so what do? Do you divide by 50? Do you multiply by 50?
Divide.
We do not divide by 50. This is the diluted answer. You diluted it 50 times, you took out a sample, measured it. So what do? Multiply. We multiply by 50. Okay? Because we diluted it 50 times. So it's 50 times less than your original sample. So we multiply by 50, we get this value. We get 2175. Okay, so how should I report this value? How many significant figures? What about this? 1. So it just reads as this. What happened now? What happened to the sensitivity of my method? It reduced it tremendously. I cannot detect a small change anymore if I'm going to round it that way. Okay, but my volumetric flask has its own accuracy. So the volumetric flask, it's not 50 ml like that. It is 50.0. I can trust to the first decimal. Okay? I have certain accuracy for my volumetric flask that I use. So I incorporate that in my equation. So what is the accuracy, what is the sensitivity of the tool I use to dilute? So now I can use 3 figures. Now I can report as 2180 micrograms per ml. Now I gain back some of my sensitivity. Okay. So in the lab, whenever we have set of data, we're going to go over, well, especially the first lab next week, we're going to go over significant figures based on the tools that you are using. And then sometimes we also have to use common sense. And we will tell you when we wanted to use common sense in terms of number of significant figures. Reporting your results in terms of rejecting data. So sometimes, like I said earlier, last time maybe, that you have replication, 4, 5 reps, 6 reps. And then one of the samples, one of the measurements look really odd to you, very high or very low. A different group member prepared it, a different group entirely prepared that sample. So a different set of errors. So you go, if I include this data point, I'm messing up my percent relative error, I'm messing up my coefficient of variation. That means low precision, low accuracy. Then there is a way to actually see if you can reject that data point statistically. You just don't look at it and eyeball it and say, I don't like it, I'm going to throw it out. Don't do that. So you want to do that statistically. How do you do it is you calculate the measure, we call it Q value. So the Q value, you take your outlier, the data points that you think is outlier, and you subtract from it the closest data point to it. So any value that is closest to it. And then you divide by the range of your data. That means the higher measurement, subtract from it the lowest measurement. And then you get a calculated measure. Then you go find a Q table, like a T table, you have a Q table, and you say, I want to look at 90% confidence. So you will have, depending on your number of observations, so you get your degrees of freedom, and you go, if I have 5 replication, my degree of freedom would be 4. Then my Q value for a 90% confidence is 0.76. If my calculated value is greater than 0.76, then I can reject that data point. Okay? And 0.76 is just an example for a 5 replication. You might have 6 replications, 4 replications, so you will get the correct degree of freedom and find the Q value from your table. Okay, so what we're doing next week in lab, so we're doing a bunch of measurements of water. So you'll be taking out volumes of water using different tools, using volumetric pipettes, mechanical pipettes, and using analytical balance to actually take the weight and convert the volume to weight. So basically, if you have 1 ml of water that you're pulling out, you will convert, no, hold up, I messed up. So you measure the weight, and then using the density based on the temperature of the water, you convert to volume. And then you compare the volume that you've gotten based on the volume that the pipette is telling you are pipetting. So you will measure 1 milliliter of water. It might not turn out to be exactly 1 ml. It will turn out to be 0.995 ml based on the weight and after you convert it to volume. So you'll be looking at accuracy and precision of the different analytical tools we'll be using, and we'll look at the set of data together and analyze those at the end of the lab. So please read chapter 4 in the book, chapter 2 in your lab manual. We're using the lab manual, so please bring that with you. We're going to go over lab safety and sources of errors in the lab, so make sure you read those documents. They're on Canvas. There will be a pre-lab quiz as always. Make sure you complete that. Bring your lab manual, lab notebook with you to the lab. Anytime I can come up and check your lab notebook. For grading, we need laptops. Each one of you will be using their own personal laptop to do the calculations. So bring your laptops with you. If you don't have a laptop, we have 5 or 6 laptops for teaching that we can pull up for you, and you can email it to yourself when you're done. So this is an individual activity. You'll be working in groups of 2, but the calculations and recording of the data, again, it's individual activity. Are we meeting in 23, Cindy?
Yeah, no, let's meet in 65. Can you try it?
Okay, so we are going to meet directly in the lab 65. And we'll go from there if we need to go anywhere. Yeah, and please come on time, because a lot of the things that happen at the beginning of the lab is explanation of what you're doing. So do not come late, please. Okay. You have 15 minutes to start a new topic. Come back! Come back! What happened? I leave you for 2 seconds. We're starting a new topic. All right. This is one of the most integral components of food analysis. Okay? Sampling and sample preparation. If we mess this up, throw away your data. Means nothing. So sampling and sample preparation, we'll deal with it throughout the semester. Practically, we'll deal with it in the lab. So I will introduce it today theoretically. Okay. Let's read this together and give me an answer. What makes sense to you? Michelle.
Letter C.
C. C is correct. Anything else stands out for you? Amanda. Amanda goes with all of the above. What were you going to say, Paige? Paige has it right. We're going to say B and C. Correct. The first one, it tells you that we're measuring the whole lab. What if you're producing 100 tons a day? Are we going to take all of the 100 tons and take them to the lab and assess the quality? We cannot do that. Okay, so often, most of the time, 99.9% of the time, and the analysis does not allow us to do this. There is a a certain analysis that allows us to scan everything, like metal detection. All of your sample goes on the belt and get detection of metal. So it's obviously non-destructive, and all of your product goes through that assessment. So B and C is correct. For sample preparation, prior to analysis, the following is true. First of all, do you know what mesh size is, or mesh number? Have you heard this term? What is it, Holly? Do you remember?
Yeah, it's like the amount of openings that a sieve has in a square inch, so it measures particle size.
You are 99% correct.
I'll take it.
So it is the number of the square opening, there are usually squares, opening in a linear inch.
Oh,
So it's not a square inch. So it's a linear inch. Okay. Just guess. And you might not know this, but guess. Do you think you should eliminate enzymatic activity? Paul?
I'm gonna say 80.
So you're only going for A. Okay. Anybody? Sammy? You were going to say none of the above? Oh.
Maybe not.
William?
I say C.
What is it?
C. Like cat.
C? Like Kevin. Okay. All right. I'm looking for the correct answer as of now. Go for it, Anne. All the above. I'm still looking for the correct answer. One, no?
B and C.
Thank you. You guys, I'll get you later.
Sure.
Yes, it's BSE. Definitely you don't want any enzymatic activity. You will change the nature of the sample. You will change the composition of the sample. So you don't want that to happen. You don't want lipid oxidation either. You're changing the flavor, you're changing the composition of fat. You are doing things to the sample that you don't want. Here, I know this one is tricky. You wouldn't know to what mesh number, but 20 is the regular mesh number. But for extractions like fat extraction, you want to go with smaller particle size. So you go with higher mesh number. Higher mesh number is meaning smaller particle size. So you have more holes in one linear inch. That means your particle size will be smaller. So for fat extraction, for example, it's recommended to do 40 mesh size rather than 20. 20 is for moisture, protein content, moisture content, ash content. So you can grind your sample to that mesh size and it'll be okay. Okay, good. You didn't know that. It's okay. We had some entertainment here. So is it feasible to evaluate all foods or ingredients from a particular lot? We talked about it's not feasible, especially when we have that many, big number of samples or a large amount of production, unless it's a rapid method and non-destructive. So we are going through and doing metal detection throughout. So I hope it's continuing where we left off in terms of recording. All right, ladies and gentlemen. Come back. Okay, so we do not necessarily measure the entire amount of sample that we have, the entire production. So 99.9% of the time you sample. That means you take samples to test from the population. That's what we call sampling. So you take samples out of your entire population and you want them to be representative of the entire population. That means when you do the measurements, you want to be confident to say the entire population is acceptable or the entire population is not acceptable. So the samples you select are representative of the population. So that means, this is what I was saying, accurate estimation. That means your representative samples should provide you an accurate estimation of the quality that you are assessing, based on which you make a decision. So what helps with the accuracy of estimation is the number of samples you pull out and how you select your samples. So what methods of sampling you get. Is it random sampling? So we'll talk about random sampling versus non-probability sampling and so on. So the sampling method and the number of samples you need to select so that you reduce variance and you have more accurate and affirmative conclusion that represent the entire population. So in order to do that in confidence, you start out with a sampling plan. So you lay out your sampling plan before you start testing. So if you are going to do the project, the first thing that I tell you to include for every step, ingredient, processing, and end product, is what is your sampling plan. So the sampling plan include the sample size. And by sample size, I don't mean the weight of the sample or the volume of the sample. I mean how many samples you're going to pull out. That is your sample size. So you have to determine sample size. You have to determine sampling procedure. How I'm going to take out my samples, and I'll give you procedures in a minute here, the different procedures that we use. Sampling procedure, you're going to use statistics, random, non-random, or mechanical or humans that will go pull out samples. So what is the sampling procedures? And then there is the sample preparation. How are we going to prepare our samples to ensure accurate and low variance results? The sampling plan also includes storage plan and transportation plan. How are we going to store the samples? So you took the samples, prepared them for analysis, but you're not going to measure today. You spent the whole day sampling. You're going to measure tomorrow. So under what conditions I'm going to store my samples? Do I need to preserve it from light? If I'm measuring certain vitamins, yes, I want to ensure that it is stored in the dark. For instance, am I worried about temperature, rise in temperature or rise in moisture? I want to make sure that it is sealed, flushed with nitrogen, potentially to reduce any oxidation. So how I'm going to store the sample is very important, because the way you store the sample will impact your results. Transportation plan, if you pulled out samples, but your analytical lab is 30 miles from the plant, because you might have your R&D or analytical plan at different location. So how am I going to transport the sample? What containers I'm going to put it in? Maybe I need a refrigerated truck to take my samples, especially if I'm looking at micro, for instance. So storage and transportation is part of your sampling plan. So factors that affect the choice of sampling plan, and here I put in red define. That means define your sampling plan. Everything I just said 5 minutes ago is what's the definition of sampling plan, what does it include? So if I ask you in the test, what is your sample, what does a sampling plan mean, or what does it include, you want to make sure to talk about all of these points. So choosing a sampling plan, that means choosing the number of samples you need to pull out, where you're going to get your samples from, how you're going to measure them, how you're going to store them. All of this, you have to know certain things, like what is the purpose of the inspection? Are we looking to accept or reject a lot? That means, are we looking for something that might impact the safety of the consumer? Or are we just looking at a quality measure? Protein content, moisture content, color, or are we looking at something more serious, like will impact health, amount of pesticides, for example. So that determines how many samples, for example, you need to pull out. Nature of the product, is it homogeneous or heterogeneous? If we're looking at flour, it's homogeneous products, all flour. If we're looking at a more complex food product that has different components, it's heterogeneous, then we need to think about how do we want to homogenize it first before taking out a sample, or maybe taking out a sample from different locations if the product is not homogeneous. and so on. So this is table 5.1, page 64. It's good to look at and familiarize yourself with what factors. So if I ask you in the test, what factors impact your sampling plan, so you can select any of these factors and explain them a little bit. So nature of the test method, is the test critical or minor? That is the same example I told you. Somebody going to get sick. Does it have mycotoxin contamination? Or is it just looking for quality? Is the test destructive? Or is it non-destructive? If it's destructive, we want to be careful for the amount of sample we want to pull out, because obviously you want as minimum amount of sample as possible, so you don't use a lot of samples from your actual population. So, and the nature of the population, how big it is, are the different lots consistent, are they small cans, you're producing small cans, or producing boxes, or you're producing flour in bulk. Okay, two last things before I let you go is the difference between attribute sampling and variable sampling. So attribute sampling is for randomly distributed attributes. That means attributes that are not homogeneously distributed throughout your product. So microbial contamination or fungal growth or mycotoxin, they might be located in certain parts of the food, not in all of it. So you need to, in this case, have a large sample size. That means you need to take a lot of different samples from the population to ensure that you screen all of the possible locations. So that means here in this case, an example is to check the presence or absence of a variable and then decide acceptability. Example could be Clostridium botulinum in canned goods. Is it there or not there? If it's there, you reject it. So organism of concern, you measure presence or absence. You get, if it's present, you get two classes. So either if it's present, there is zero tolerance, that means more than zero, you reject. So if there is any, it goes to reject. Count is zero. No more than zero count. If there is a different organism or a different component of concern, like a residue that is of concern, like a pesticide, what would be the concentration? If it is within the allowable concentration, you accept. If it's over the allowable concentration, then you would reject. One minute, and then we're leaving. Variable sampling, this is for normally distributed attributes. So those are the attributes that are equally distributed in your sample. For example, moisture, or ash, or fat, or protein. They're present equally wherever you take a sample. They will be in the same concentration if you homogenized your sample. So in this case, you don't need large amount of sample or large number of samples to pull out. Just a small number of samples to pull out because the attribute is normally distributed. And it's mostly for quantitative analysis, where you are looking for concentrations or quantity on a continuous scale, and then you decide acceptability based on the quality specifications that you have compared to an acceptable value. So color, total solids, salt, protein, moisture, fat, all of that. Okay, I'll let you go.